Hello everyone, my name is Yin Liu. I'm from Virginia Tech. Today I would like to talk about my GPCE paper, VarSem. Our title is Declarative Expression and Automated Inference of Variable Usage Semantic. So what is variable usage semantic? As everyone knows, if we want to understand a book, we need to first understand its words. Similarly, if we want to understand a project, we need to understand its variables. How are they used and what do they mean? We call this variable usage semantic. Understanding variable usage semantic can help software engineering and security domains, such as program comprehension, code audit, and vulnerability detection. Our idea is from a philosopher, Ludwig Wittgenstein. He says the meaning of a word is its use in the language. That means when we want to understand a word, we should not only focus on its textual information, but also we need to know how it is used in the language. So similarly, when we want to understand a variable, we also need to consider two parts. First, symbolic name, that is a variable's textual information. And second, how it is used in the program, that is a variable's context information, for example, its data or control flow. Let's look at an application scenario. Say I'm a programmer, and my manager told me that your task is to protect user password. What should I do? First thing I need to know is how to identify password variables. A simple way is to use some string match. For example, I can use Ctrl+F on a given project source code and search some variables name. Maybe his name is the English word password. But it doesn't work. We did an investigation on GitHub and found that the names are very different. For example, the name PASSWD has 11 million cases, and P-WD has about 9,000 cases. Some variables has a single letter name, P, and some variables name is irrelevant string, such as ABC. So as the programmer, I don't know how to identify the variables that store the user password. To address this problem, we create a domain-specific language, VarSem. VarSem enables developers to define some rules. One type of rules can represent a variable's textual information, and the other type of rules can represent variables' context information, for example, data or control flow. By combining both information, we calculate a likelihood for each variable. That indicates how likely a variable would store the user password. For example, this variable char password has 95.7% to store the password, and this variable in the P has only 0.3% to store password. So based on this result, developer can easily identify the password. Let's look at an example of VarSem syntax. We have a semantic category, and inside this category, we have several rules. First rule means we want to figure out some variables whose name is close to password, and its type must be able to store textual information, such as string, and its value must have flown from some user input. We run these rules on some code files and give them a threshold, 0.8. That means after we calculate the likelihood, we select the variables whose likelihood are greater than the 0.8, the threshold. and use these variables as the final result. For each rule, we can give them an impact value, because when we calculate likelihood, we need to consider these 3 rules. So we need to use weighted average. This impact value is the weight, which controls calculation of weighted averages. We also can bind a specific analysis routine to this rule. And this analysis routine will calculate likelihood for this rule. Let's look at VarSem Overview. As a programmer, I can first define a semantic category, which includes several rules, and I can add, remove, update rules in this category. And then I can bind rules to analysis routines in VarSem library. I can also create new analysis routines. Finally, I can run these rules on some program files and got results to analyze. Let's look at how can we execute VarSem programs. Say we have several rules from N to N. We first generate information vector for each rule, and then we execute each rule one by one to get the likelihood. After that, we based on each rule's impact value to calculate the weighted likelihood for each variable and use this as the final result. To implement VarSem, we use some techniques. First of all, we use Scala as the host language for VarSem. Scala is a very flexible language, so it makes VarSem's library easier to be extended. Also, it makes VarSem platform independent. We also use LLVM as our analysis infrastructure. We use it to extract the information of variable and also perform data flow analysis. Our VarSem library also provides several built-in analysis routines. For tongue test information, we provide some existing data flow and control flow analysis. For textual information, we provide an NLP-based analysis. In this presentation, I will focus on NLP-powered analysis. So our NLP-powered textual analysis has several rationale. First, function matters. Let's say a variable pwd in a function login. That means this variable are more likely to store the user password. But if another variable with the same name pwd is in the function unix-shell, that means maybe this variable will store some information related to pwd command, which is the Unix shell command. And second, type matters. We know that developer can give a meaningful name for some composite data types. So let's say a variable has a struct type named password-info-t. That means maybe this variable will store some information related to password. And third, adjacent words are semantically connected. Let's say we have 2 file paths. The first path, the password folder, is close to the code file x.c. And the second path, the password folder is far away from the code file. So let's say a variable is in the first file path. That means this variable are more likely to store some password information because the password folder is closed to the code file. Let's look at the analysis process. Because usually a variable's name has some specific format. For example, A-B-C or A capitalized B, C capitalized D, E. So first of all, we need to split and combine them to several arrays for future analysis. We also need to remove some redundancies. For example, the name, the-password, because the is not meaningful, so we can remove it. Let's look at the entire process. Say we want to run this rule. We want to figure out several variables whose name is close to password. And here is variable's information. Its name is pass-word-info, and type is struct information in function login, and file path is src/login.c. After preprocessing, we will get several arrays. Each array is for the first array is for the variable's name, and second array is for type, and third one is for function, and last one is for file path. Then we will calculate similarity between the target word, password, and arrays. We do this for each array and got similarities. Then we find the max value and use it as the similarity of variable name. And we do the same thing for type, function, and file path. Finally, we will add them together and normalize it, and use the normalized value as the variable's likelihood. To distinguish the adjacent word in file path, when we calculate the similarity for file path, we will multiply a attenuate rate lambda. That means if the folder is far away from the code file, its similarity will get smaller. Let's look at our evaluation. The first one, correctness. To evaluate correctness, we include 8 real-world projects. These projects access several personal information, such as SSN, phone number, password, etc. And we write VarSem rules and programs to identify the variables that stores this personal information. So it turns out VarSem, our solutions, has a satisfactory result of accuracy, precision, and recall, because we consider both textual and context information. So our performance is better than the solution only considers the textual information or only considers the context information. Besides that, we also evaluate a bottom line. It's a simple string match function. Our performance obviously is much better than the bottom line, the string match function. To evaluate effectiveness, we found that a framework, UbicoPan, has been subjected to 2 security attacks. The first attack is the attacker can exploit a particular password string to circumvent the authentication process. And the second attack is the attacker can exploit an enclosed file descriptor to leak or tamper with data. So we evaluate these 2 scenarios. First, identify the variables that store password. And second, identify the variables that store file descriptors that has not been closed. So our result tells us for both scenarios, if we have a suitable impact level and reasonable threshold, our solution can give developer a very good accuracy, precision, and recall. And finally, we also evaluate programming effort for VarSem. So it turns out to write VarSem program, we only need to write about 6 lines of code to handle all the evaluation above. If we want to use Unix style, we have to write about 16 lines of code. And all the relevant routines are about 2,000 lines of code. That means VarSem has a very small programming effort. And that's it. Thank you for your attention. If you want to get more details, please read our GPCE paper. Thank you.